Hello everyone, welcome to the ninth session of the quantum field theory. Today we're going to talk about Dirac propagator. Dirac propagator is the expectation value of the two-point correlation, which is equal to the green function of the classical theory. The left-hand side is a quantum mechanical object. It's a quantum mechanical operation. Here you can see on the orange, you have basically operators and you can use the quantization of the field to find the expectation value on the left-hand side. But on the other hand, on the right-hand side of the equation, you have a classical entity or the Feynman green function. But we're going to see what is this green function. It is equal to Heaviside function of x0 minus y0 times the retarded green function plus the Heaviside function of y0 minus x0 of the advanced green function. So retarded green function is the correlation between now and past, and advanced correlation function is the correlation between present and future. So as we said, past and future are two allowed direction of time. So we have to have these two both contribution from past and future summed up together with some Heaviside function. In QFT, in electrodynamic and in mechanic, time is allowed to go forward and backward. So if we say x0 is present, then there is a light cone here, and this light cone extends to future and past. And there is not a fundamental difference between future and past because you can always interchange the sign of the time. Again, if I sit in present time and if I call x0 present time, I can have two types of correlation. I can be correlated to the fields in future and also the fields in the past. So I can say there might be a causal connection between x0 and y0, and that's why you have these two terms here, because this y0 can have two possible ways. One can be future and one y0 can be past. So there is always forward time and also we have backward time, and it is very similar to positive and negative frequency answer. So two possible ways are allowed and kind of symmetric. But again, remember that in thermodynamics, we have one-sided arrow of time and we are only going into future, and any effect is propagating from present to the future. So it looks like that when you have thermodynamic, you have a one-sided light cone. But the deterministic theory like electrodynamic or quantum mechanics or even classical mechanics are invariant under the change of the sign of the time. So just pay attention to the difference between these two effects when you have only future in thermodynamic, but in most of the microscopic theory, you have future and past. In order to have the correct propagator, we need to have the time ordered of the two fields. So we should talk about time ordering operator. So this time ordering operator mathematically is defined as if you're giving two fields, for example, psi of y and psi of x into the t operator, the t operator looks at them and try to categorize them in two categories. One x0 is larger than y0 and one x0 is smaller than y0. And then if x0 is larger than y0, it would just put psi of x first and then psi of y. And the reason is we want to preserve the causality. So if x0 is larger than y0, x0 is the future of y0. So psi of x should be final state and y0 should be initial state. But you can always interchange them. There is no difference between them. You can always say backward and forward terms are interchangeable. But the point is, when you put psi of x0, or let me say psi of x, psi of y, you're just paying attention that x0 is larger than y0, so psi of x is going to be the final state, and that would be on the left hand side. So the logic of time ordering is just simply to see which one is happening after the other one, so we put it on the final state effect. So that's called time ordering operator. So the correct propagator is a time ordered propagator, not only just multiplication of two fields. It should be the time ordered of the two fields. Okay, so let me write down the Dirac equation. So this is called homogeneous Dirac equation. This is what we solved. And homogeneous Dirac equation is not always the case. So there are cases that you have not zero, but you have any arbitrary function of space and time. This is called external current, or something that you put it there in order to get coupled to your field. So your field naturally is a free field, but you can also get coupled to it if you put this j of x there. And this j of x is going to be like electrodes. So imagine this is the space-time volume that you're really caring about, and you have your field here, and then imagine you have some very fine-tuned, very hypothetical form of electrodes that are allowed to inject some current but the current is in the dimension of psi of x. It's not electrical current, and somehow stimulate your field. This is similar to neurobiology, right? When people put these electrodes and they inject electrical current to the neural network in order to stimulate them. Well, so now the question is, if I have some form of controlled current, how can I find the answer? So let's answer to this question by having some assumption. So there should be some assumption, and these assumptions are going to make our job easier, or there are certain form of approximation. They are not exact solutions, but they are approximation that you think can happen. So now let me write down the first assumption. My field is the sum over another variable y and some function, I call it g of x minus y. There is a good reason why x minus y or y minus x, just the difference between the 2 points. And I put this index f to say it's a Feynman propagator times j of y, and that j is the current. Well, this assumption means that I can write down my field as a response to a current. If I can imagine there is a linear response from current, which is g of x minus y, I have a kind of linear operation on my current to get my field. So the first assumption is that a linear response to my current can give me my field, and my job is to find the green function or that response, a response function. Now we will see why it makes it easier. Now I put this definition of psi of x into the Dirac equation, and since integral is a linear operation, I can take the integral out, and I just write down g of f times j of y times d4 of y. This is equal to j of x, but I write j of x as j of y times delta of x minus y. Well, this is not just a mathematical trick. I want to turn the two sides into an integral of the same variable so I can get rid of them. So now you see how it's going to be easier. So the Dirac operator, or the derivative operator in the Dirac, is with respect to x, not with respect to y. So now I turn my variable into y, then I only have the derivative with respect to x only acting on the green function, not on the source. So that's how I can get rid of my source and cancel out the source from the two side, because again the Dirac operator is derivative with respect to x, not with respect to y. So now I can see how everything can be factorized out. The current can factorize out. And see, this term only acts on this, not on the next term. So I can take out j of y out of that operator. So I have j of y, I can take it out, and then I have the same Dirac operator here, but only acting on the green function, and that is equal to the delta function and the current. Now it's good, but look at this. Now we can get rid of the source, because if we assume source is non-zero, so we can cancel it from two sides, now we got rid of source. So our solution is going to be independent from the source, and that's amazing, right? So g of x minus y is equal to, so the Dirac operator of the green function is equal to delta. Now, I don't even have the integrals because I got rid of y and I got rid of source. And now I want to find g of x minus y. So I cannot just simply divide it, because this orange part is an operator, right? It's an operator. So now it's the next step. The next step is to make that operator to act like a fraction, and that's when we can expand g of x minus y into a Fourier mode or Fourier transformation. Then the derivative with respect to some exponential term is just going to take out the momentum. We did it 100 times in quantum mechanics and Schrodinger equation. So I can write g of x minus y as now the summation over all possible four momentums of some g tilde of p times exponential of p dot x minus y. And this is the famous duality, that any length difference can be translated into a momentum, but one single momentum. So we take x minus y into p, and wavelength and momentum, now we see the duality between them in uncertainty. And maybe I can give you an example of the FM and AM radio. When you have FM radio, you have short wavelengths, and when you have AM radio, you have long wavelengths. So any distance can be translated into the state of the momentum. But then again, pay attention that Fourier transformation is also an approximation of the free fields. So that exponential term here are free waves or free fields that are like sine and cosine function, not normalized, and they are just, monochromic, so they have only one frequency. So these are free plane waves answer, and these are the answers from homogeneous part. So that's why when homogeneous part becomes important, because the answers of the homogeneous part is giving us these Fourier modes. Now, since I expanded the green function, I should expand delta function in terms of momentum. So we can write down the delta function as the summation of this exponential term over the proper normalization, 2 pi 4 and d4 of p. And now, if I put these two equal, I'm going to have I gamma mu d mu, the Dirac operator, acting on the integral of the d4p to pi 4 g tilde of p exponential of I p dot x minus y equal to the integral of d4p, same thing, exponential. And now I can apply this Dirac operator into the g tilde that times that exponential term. So g tilde is a function of p, it doesn't do anything on that. So I'm going to have I gamma mu minus I p mu. Minus I p mu is coming from the exponent of the exponential. So, I'm taking a derivative with respect to the muth component of x. So the muth components of p is going to come down. So I would have this operator acting on g tilde. And those exponential terms are going to cancel out. So I'm going to just write down for now. And we have the integral over d4 of p on the left side over 2 pi 4. And then I have the same integral on the right hand side. And now, I can cancel out those exponential terms and get into the final equation. So I can calculate the g tilde of p is equal to 1. So now I can write it down as gamma mu p mu minus m. Right? And I'm going to multiply it into the same numerator and denominator. So I'm going to just multiply it by the conjugate version of the denominator. So the denominator, I'm going to use the identity that it's going to become p squared minus m squared. This p squared is p0 squared minus p vector squared. And the denominator is going to become gamma mu p mu plus m. Okay, so now I got the g tilde of p, and now I need to put it into the integral to get g of x minus y, because that's the green function. So, we want to find that. So that is equal to, now integral over all momentum, R4 momentum. And now I can write down g tilde. This is g tilde. And then I have the exponential term. And now this is green function, and green function is propagator. So we have the form of it. We have the integral over all momentum of some terms that are function of momentum. So that's it. This is like a propagator expanded on the momentum state. So we diagonalize basically the propagator, but we just found the green function from classical equation. But now we can do one more step to more simplify it, and is to perform the integral over the p0. But let me note something. The integral of d4p is not only limited to the on-shell contribution. So sometimes we have this constraint to say we only want to allow on-shell particle to propagate. So we put this delta of p squared minus m squared there. But now we want to calculate the Dirac propagator of anything. So that would include the particles that are not on shell. So that's why this d4p is just some open integral. So now I can do one more step forward. So I'm going to separate the space component of the momentum d3p from the integral over dp0. Sorry, this is 2 pi only. And then I want to see if I can perform the integral over p0. So I have all the term here. But that's a kind of challenging integral. This is a challenging integral because, well, when you have this form of integrals, you might not really know how to solve it. Well, you have an exponential term, and then you have p squared in the denominator, and you have some momentum with the gamma matrices. So it's not really easy to calculate this integral, but some technique is going to help us to calculate that integral, and that is complex integrals. So you have some functions like this, 1 over x squared plus a squared, and even sometimes you have this exponential term here, I k of x t. Well, t is not really important here. I can just erase t here. But imagine you have such an integral and you want to calculate it from minus infinity to plus infinity. To solve this kind of integral, you can use a trick and you try to use complex integrals in order to get the answer in a second without really calculating that huge integral. So first we find the roots of this equation, and then we see the roots are plus or minus ia. So if we imagine now x is not a one-dimensional number, we turn it into a two-dimensional number or a complex number. This magenta axis is a real axis. I mean, this blue axis is a real one that we want to perform the integral. And the roots are located into the imaginary axis. So if we think x goes to z or x goes to some I plus ab or a complex number, then we can extend this integral to a one-dimensional closed path. This is called a contour, and it lives on a two-dimensional, again, surface of the complex numbers. And usually contour is closed counterclockwise. And if you have a singularity in the contour, it's your heaven, because that singularity is going to help you to find the integral on that contour. This is amazing. This is something incredible. I mean, imagine you want to find the integral on the surface of something or the boundary of something, and all you need to know is the value of something at singular point. So that's basically like a black hole. That singular point has all the information. This comes from the residue theorem. So the residue theorem is the theorem from 19th century, from 1800, by Cauchy. Even before the quantum mechanics, 100 years before quantum mechanics, Cauchy was a French mathematician who were developing theories about the complex numbers. So his theorem is similar to the divergence theorem in physics. So imagine f of z is an analytical function, which means that it can define derivatives in all points of that. So in all points of some, closed path, f of z is analytical in all part of the contour. Okay, so imagine this is the complex number coordinate, and this is the contour. So it's just any contour can be a closed path and counterclockwise. And imagine f of z is analytic over all that area. So if I calculate the closed integral over this contour, the answer would be 0. Similar to the divergence theorem, again, if you don't have any net charge, the flux would be 0 for a surface. But Cauchy theorem is not going to be useful here. Another theorem is when you have some functions like, imagine f of z is some g of z divided by some x minus a, or sorry, actually it should be z minus zi. And this zi is a number, and I have this symbol here for the multiplication, is like sigma for multiplication. So imagine I have, so I'm trying to make some artificial roots in the denominator. So z minus zi are roots. So we have, for example, multiple poles in the denominator. Imagine it extends to z minus zn. Imagine we have n points that basically have a singularity. And this singularity order is determined by this m number. That's the power of those terms in the denominator. And this m can be seen as the order of singularity. So you can kind of just quantify how fast or how rapid you approach singularity when you get close to it. And the residue theorem is going to be this. So imagine you have such a function and you try to calculate the integral of some g of z. So g of z is the analytical. It's well behaved, and it doesn't have any poles or singularity. But imagine again you have something like g of z divided by a multiplication of series of first m order poles, right? That I just symbolize it like that. So if you want to calculate such an integral, let me visualize it. So it's a contour. And imagine inside of this contour you have these poles. You have these singularities. You have these black holes. And the order of these singularities are not necessarily the same. So when you're approaching them from different, radial distance, the way that we approach the value of the function is going to be, different for them. So I can just show different colors for different flows anywhere. So these are all singularities. These singularities are going to help us to know the answer of this integral, and the answer is the sigma over all I, or all singular points, of some mysterious things that we call it residue of function. So imagine I call this whole thing f of z. So the answer would be the residue of f of z at the point of zi. So zi is the singular point. So what is the residue of some function at some point? Sorry, I have 2 pi over I. So this 2 pi over I is there for some conventional reason, because we're integrating over a kind of circle, because it's a closed path. So you put some 2 pi over I. But the important part is the sum of residues. So the sum of each residue. So the residue of a function at point z of a with the order of m. So I should also put the order of m here also in the residue, because it's important. What is the order of m? What is the order of singularity? So the residue of a function of f of z at point z of I with the order of m is going to be the limit. So it's a limit, like high school limit. The m minus 1 derivative. So this m is the order, same order. M minus 1 derivative of what? Of the function times the z minus z of I to the power of m. So m again is the order. So you see what we are doing. We're trying to multiply the function into z minus z of I in order to take out the pole and then take a derivative at that point and then take z to z of I. So that would be a well-defined limit. And this is called the residue theorem. And it's very beautiful. So now we're going to see how it's going to help us to evaluate that integral. Now, what do I want to solve? I want to calculate this g of x minus y on top. And I have an integral over dp0. And the residue theorem is going to help us to calculate that part, dp0. So let me just copy that part and paste it down here. So I want to calculate this, right? I want to calculate this blue integral. So I can look at this part as the integral of this, there is this exponential term. You remember I said there's functions like this. So that function is similar to that. So I'm going to use the residue theorem to solve it. Now let me again write down the integral. But I'm going to separate the terms here. So I have this term here. I have the denominator. Now the exponential term, I'm going to separate the 0th component, dp0. Oops. The 0 is the upper index. And exponential of minus ei p dot x minus y. Okay, I'm just separated this from, these are like p0. And also there is a p0 in this phrase, gamma mu p0. But, I'm just going to leave it there. Yeah, so this integral is complicated. And how to solve it, find the poles and use the residue theorem. So where are the poles? The roots of denominator. So p0 squared is equal to p squared plus m squared. So we want to find the p0s that the denominator is 0. And that's super interesting because these are the on-shell condition. So if p0 is plus or minus the square root of p0 squared plus m squared, or plus or minus omega p of on-shell particle, this is where we have a singularity. That is very interesting because the singularities is coming from the particle which their 0 component of momentum is equal to their momentum plus their rest mass. So if I again think that now p0 is my variable to integrate, so I have imaginary p0 and then I have real p0, and I'm talking about real p0. I want to perform the integral over real p0, but the poles are here. Now this time the poles are on the real axis. So I have omega p here and I have minus omega p here, and I want to take the integral over this yellow axis. Okay, and that would be complicated because now I'm actually crossing by those singularities, and you can't just integral over singularities. So I need to go around them. I need to move them a little bit and then use this residue theorem. So there is this trick that you can move your poles from your real axis because you want to integrate over real axis, and well, it's not good to have the poles on the real axis. So you try to shift them, and when you shift them, then you can close a contour around them. So that's just the philosophy. So imagine I add this term I epsilon, and then I try to factorize the whole phrase into something like this. So, I can have P0 minus, no, sorry, P0 squared. P0 minus omega P, we define what is omega P, plus I epsilon, minus P0 plus omega P minus I epsilon. And if we imagine epsilon, second order epsilon is, 0, then, by the first order you can accept that shift. And, there is a plus and minus sign here. So that shows the poles are, going into the different directions. So we are shifting the poles, but one of the poles upward and one of the poles downward. Actually, we're going to say which one is upward and which one is downward. It's actually the opposite of what I draw. But anyway, this trick is going to help you to evaluate this integral. And then you say, what should I do with epsilon? Then you can take it to 0. Don't worry about it. So I have everything the same. So I have the denominator here. So the denominator, I'm just going to write it down as, the factorized term. So I have the first term here, or the positive frequency term, and the negative frequency term. And both of them are, again, on-shell particles with positive and negative frequency answers. Now this is the trick. So this integral, the real integral, is equal to the complex integral. So imagine I'm integrating over dp0, but dp0 complex, not just the real one. So I have this contour integral, and this function here inside of this yellow box is that f of p0, and this f of p0 is a function that has the singularities, and we see the singularities are those 2 points on the unshelled condition. Anyway, this contour integral minus the contribution that is coming from the circumference of this contour. So imagine this is 2-dimensional P0, and this is one of my poles slightly above the real axis, and I close the contour here. So here, imagine I have this contour, and it looks like a circle. We want to make it like a circle, and there is this radius r. And we are taking this limit of r to infinity because we are allowed to, close the contour. But, the point is that we are integrating from minus infinity to plus infinity. So eventually r goes to infinity naturally. So this green part on the circumference is the contribution from that term. So we can say the real integral is equal to the complex integral minus the contribution that comes from the circumference of this circle when r goes to infinity. But the beautiful point is that this term is equal to 0 at infinity, and you can simply write it down because the function kind of decays at the far distance. So if you go far and far, these functions become 0, and then the whole integral converges to 0. So the circumference term is 0, so therefore the complex integral is equal to the real integral, and that's as simply as that. So this complex integral is just equal to the integral that we want to calculate, the real integral. And again, that specifically happens when we have a function, for example, that has 1 over p0. So if you go to p0 that is large, the contribution of the circumference is going to be 0. So all I need to do is to just write down the integral in the form of the complex integrals and use residue theorem to find out the answer of this complex integral. So you have all the terms, I'm just rewriting them. And I'm just writing down this p0 term with another color to emphasize that the integral is over p0. And there are two possibilities. Now I want to calculate this integral, but there are two possibilities. There are two distinct possibilities, or there are two orthogonal possibilities, whatever you want to say. Well, let's say two possible way. But anyway, I'm just saying that there is a condition that could not be met at the same time for these two possible way. So it depends on the sign of x0 minus y0. So one possibility is that x0 is larger than y0. So x0 minus y0 is larger than 0. So when you want to calculate exponential term that has ip0, x0 minus y0, you have to remember that this p0 again right now is a complex p0, and when we go up into infinity, we are going into kind of I infinity. So there is this I term here, and there is I P0, and P0 itself is a complex. So we want this exponential term to be convergent into 0 when it goes to infinity. That's the kind of behavior that we kind of expect. Because otherwise, this integral is going to be a divergent integral. So again, imagine this is the first pole. Let me have some straight lines. Okay, so I have these two poles here. One of them is omega p minus I epsilon, and the other one is omega p plus I epsilon. And we're going to show why both of the singularities are not contributing into the integral at the same time. So because they have two distinct answers. And from the pole perspective, so there are two types of particles, but from the time perspective, if x0 is larger than y0, then to make this term minus I p0 times x0 minus y0 converge into a minus infinity, or make the exponential term to converge into 0, I should take this p0 to plus I infinity, or I should close this contour upward. Again, just to converge that exponential term. So when I close the contour upward, only one singular point, which is omega p plus I epsilon, is going to be inside of this contour. And I can use the residue of the function at that point to calculate the integral, and I should close the contour upward for the case when x0 is larger than y0, or you can say x0 is the future of y0, or y0 is in the past of x0. So the other possibility is that x0 is smaller than y0. Then to make this term converge, I need to take p0 to minus I infinity. It's the opposite way, because again, x0 minus y0 is negative. So in order to make this term goes to minus infinity, I should close the contour downward. And when we are closing the contour downward, the other pole in the green contour is going to be, the only one pole in the contour is going to be omega p minus I epsilon. And yeah, that's the logic of it. There are two cases, and you have two distinct ways of solving them. And your final answer is the summation of these two terms, or these two possibilities, with those heaviside functions, in order to activate them in the correct time when x0 have the proper relationship to y0. So now let's do one of them, use residue theorem. So if x0 is larger than y0, then to calculate the following integral, I should use the residue theorem. So I'm just going to write down the integral. So now this integral is equal to 2 pi I times the residue of the function, and the function only have one residue because there is only one singular point inside of that. So we are just writing down everything in order to calculate the residue. Just have to write down everything all the time. But now we just pay attention to the terms in the denominator, because this is the point that we are going to multiply this whole fraction into those terms to take out the poles. So what pole is inside of the contour when we are closing it upward? The pole which is minus omega p plus I epsilon, which now the term is going to be p0 plus omega p minus I epsilon. And I take the limit when p0 goes to actually minus omega p. So this is not omega p, is minus omega p. So let me put this minus here. Again, and the two poles are first order, so there is no derivative in the calculation of the residue. We only can use function times those terms, and then they cancel out. So and then now when we take the limit to minus omega p, this integral is going to converge into a finite value. Okay, so now let's take all the limits, and we also have to get rid of this epsilon term, because this is an artificial constant that we just added, but at the end we should take it out. So we're going to show how epsilon is going to taken out by converging it to 0. Okay, now I set the limit of epsilon goes to 0 of 2 pi I, 2 pi in the denominator of the original integral. So these 2 pi's are going to cancel out. And then minus 2 omega p from replacing p0 to minus omega p. There is also this epsilon term plus I epsilon here. which is gonna taken out by taking epsilon to 0, and then on the top we have these Dirac terms and the exponential terms. Now here, instead of p0, I'm gonna put minus omega p plus I epsilon, and then I have the time difference. Now we take this epsilon to 0, so no problem, and we already converge, and that is equal to, I'm just gonna summarize it very quick, minus I. So I'm gonna try to put this minus I on top and make the denominator positive, and everything else is the same. So this is the phrase for propagator, just calculating the integral, the 0-part integral. And you can see here you have I omega p because there is a minus omega p, so that would change the sign between the terms, and you can now think about that as 4-vector product of momentum and space-time difference. So that's the integral of the p0. So now if I just call this phrase I, then the propagator is going to be integral over d3p to pi 3 of I. That's propagator. Propagator is an integral over momentum. And the function that we need to take an integral from is something now is a function of momentum, and the energy term of it is on shell. So that's just interesting because we didn't enforce on shellness, but at the end, the final answer, the four momentum is emerging out because of the answer of the integral. So similar logic now can be applied to the condition when x0 is smaller than y0. This is where x0 is past of y0, or you can say y0 is the future of x0. You see there's a symmetry in definition. So we have the same integral. So that phrase I is the same, 2 pi I times the residue, but at a different point when p0 is taken into omega p. Last time was minus omega p, this time is omega p. And now we need to just take out that residue. We should take out the poles. And if we just rewrite everything else, the logic is the same, and all it changed is the sign of the p0. The other one was minus omega p, and this one is plus omega p, but you see there are different poles. One of them is plus I epsilon, and the other one is minus I epsilon. And then again, this difference between the poles, one of them is shifted upward and the other one downward, is that when we close the contour upward or downward, we can kind of isolate each of these singularities, so we have one singular point to calculate this integral. Anyway, so we saw how it works. Now it cancels out, and we take the limit, and the final answer would be exactly the same, but on the denominator, instead of having minus 2 omega p, we have 2 omega p, and everything else is the same. So just leave it out to write it. Okay, now I have this phrase, and now I can write down my green function of f, which means Feynman. X minus y is equal to the Heaviside function of x0 minus y0 of green function, which is the retard green function, x minus y. So that's for the case when x0 is larger than y0. So it's coming from y0, which happened in the past. So that's why it's called retarded, because that's the effect that comes from past to the present. So I'm going to just take out this phrase. So this is gr, and then the Heaviside function of y0 minus x0. So the bigger one comes first, and then you have this advanced contribution. So this advanced contribution is when y0 is larger than x0. So y0 is in the future of x0, but because there is also backward time propagation, there is some causality comes from that direction. So we have this retarded propagator. The retarded propagator has this minus I, and the exponential terms are different. And the fact that the exponential terms like the omega p are connected to the fact that there is a retarded potential or advanced potential, there is a connection between future-past duality and particle-antiparticle duality, or you can say the duality between omega p and minus omega p. So you see all of these dualities are consistent in the framework. So here for the case of x0 larger than y0, so I'm talking about the effect from past, we have positive omega p. So we can call positive omega p a particle. And for the advanced potential, I have all the phrases, all the terms the same, but only the exponential term, which has a minus omega p, for the case that x0 is smaller than y0. So for the effect that comes from future of point x0, I'm dealing with another on-shell condition. So I hope that you can just see how, particle-antiparticle can be connected to this future-past propagation. Now we have these phrases for retarded green function and advanced green function. You might say this is an integral, and it is not convergent because we are integrating over all momentum. And what if we have infinite momentum? So to converge this phrase or this integral in general, we can put a cutoff on probably the size of the momentum that we are integrating. So if we are just integrating numerically in the momentums that are smaller than something that you call it momentum max, or cutoff, you can call it cutoff, I can do a numerical calculation. So this green function mathematically is divergent because we are summing up overall momentum. So we start reviewing the session again. We started with the meaning of two-point correlation and the two-way arrow of time, and then we talked about this time ordered operator, and then how this time ordering is propagator, calculating the green function method, using green function expansion on Fourier transformation, and finding the green function, then putting that green function and integrating them using residue theorem. The residue theorem we learned was very effective in calculating these kind of integrals. And I integrated over P0, and then my final propagators are only function of momentum, or a space component of the momentum with the enforced on-shell condition. So this was the time ordered expectation value of 2 points of a space-time that the psi field is defined on, and this is equal to the classical sum of the Heaviside function times the retarded green function plus the Heaviside function of y0 minus x of advanced green function. And each of those green functions are 2-point correlators that we solve from classical theory. So for any x and y, which x minus y is now larger than x0 minus y0, which means that they are space-like intervals, or the intervals that light doesn't have time to travel between the 2 points, the causality is enforced, and this expectation value is equal to 0. So this time ordered, and this time ordering was, all the fact that x0 is larger than y0, y0 larger than x0, that would give us 0 to this expectation value. So we preserve causality in quantum mechanics, because if we don't do that, we don't get non-zero term. So thank you so much for watching QFD9, and in the next session we will talk about discrete symmetries, and then we are ready to go into interaction picture.